So, counting rules. Again, all we have to know is the number of ways in which a particular event will happen. Before we get into the rules, one thing that we want to understand is the concept of replacement and the concept of ordering. So this is what he was talking about. Replacement, we have two strategies. Either you could do with replacement, or you could do without replacement. Ordering, you could do it in two ways. Either ordering matters to you, or ordering does not matter. So when we collect observations, do we want it with replacement or without replacement? In the sense, suppose I walk around and I want to record your GPAs. Now, GPAs will come from a sample space. Who can tell me that sample space? So if I asked you what's your GPA, would you tell me FGCU?
Oh, no.
No.
Every possible GPA, I forget what the 0 to 4.
0 to 4, right? The interval, that would be our space where each of the observations would come from. So in that example, let's say I go around asking GPAs and recording them. Should that experiment be done with replacement or without replacement? Without replacement.
What is your replacement?
In other words, you put it back in.
Well,
So you take an observation, you put it back in.
if you have to put it, then you're going to double count people.
Well, I think you're talking about replacing the numbers, not the people.
I'm talking about the replacement of numbers.
So if someone gets a 3, then that means that like if you don't replace, then nobody else can have 3 all of a sudden.
Very good. So it has to be with replacement because I walk up to Vita and Vita tells me I have a 4.0 and I took that number, so I recorded it, so I throw it away. That would tell me that there could be no other person at this university with a 4.0. Right? Because I've excluded it. So I want to put them back. So typically, frequency statistics, when we collect a sample, it's done with replacement so that there is no bias. And that would result in what we call a simple random sample. Did I mention this last time? No.
Yeah, I think so. Maybe.
And simple random sample. I'll put it as infrequentist statistics. There is another type which is Bayesian. Frequent. Infrequentist statistics. So that is a type. If you still have that undergraduate textbook, go and look up simple random sample. It'll make more sense after you get it. Are we clear with replacement with and without? Any questions before we move on? Okay, because I'm going to write the rules soon. The next one is ordering. Does it matter? Does it not matter? So if I say order matters, I am talking about arrangements, sequences, and so forth. Arrangements, in other words, they all need to have order. Previous case, if you look at HD, TH, I counted them as separate possibilities because HD is not the same as a DH. Since I called that to be coin 1, called that to be coin 2. Same thing over here. So I can't simply switch them around because I'm very specific in saying coin 1, coin 2. I'm giving them an identity. So we can't switch them around. But if it doesn't matter, I can simply switch them around because order will not matter. Whether it's HD or TH, it means the same thing. Do we follow?
Yeah.
So, two different cases with replacement, ordering, and subtypes with replacement, without, where it matters and where it doesn't matter. If it is without, you don't put it back. Once you take, it's gone. Okay. The fundamental rule of counting that I wrote with multiplication rule will apply with pretty much any case. So we will start with I mean, all I'm trying to say here is I'm finding the total number of possible outcomes. That's all. When I say total number of ways in which they can happen simultaneously, I'm trying to find the total number of outcomes when I have k experiments, and each of them could happen in R number of ways. In a problem like this is the first thing you have to do. Let's see if you paid attention. What should I do? Do something like that. It's easier to follow. Don't just memorize the formula. So position 1, 2, 3, all the way up to k experiments. In how many ways did the first experiment happen? R ways. How about the second one? R. In total, R. How much the k ways? Things to know. This is width replacement and the order matters here, right? Because each of them is an experiment, so the order will also matter. Now, why do we say that this is width replacement? As you go from one experiment to the other, the number of possibilities for each of them does not change. You keep on putting things back, it's always on. So it is width replacement, and we always come up with unique sequences or outcomes. So automatics. We had a coin example. Let's say we'll have fun. Here is an example. A typical phone has a 4-digit screen lock. And you all have entered, numbers for each of each spot. So each digit would be a spot. How many possibilities would you have? Can take a value from 0 to 9. That means inclusive of 0 and 9. Between would mean in between. So did I say pin? And then that's for the combinations. We have all. So the typical phone has a 4-digit screen lock, and we know each digit would go from 0 to 9. So I'll do this. This is for learning purposes. Once you get practice, you can go in your head. But, I occasionally will sit and draw this out for certain cases, because when you draw it out, it will make better sense. How many was, first off, does ordering matter here?
Yes.
Yes. 1024 is not the same as 2410. Yes, or 2014. So the order matters. Should we do it with replacement? Yes, that's always. I mean, if you want an easy one, you could simply put 0, 0, 0, 0. Right. So how many possibilities do we have for the first one? 10. Second, 10. Right. In other words, we have to try 10,000 times to get to the correct password. By then, it will also work, and sometimes it will catch on fire. Depends on the code. So if someone asks you, well, what is the probability that you can have, this phone? The probability is 1 in 10,000, right? So all I need to know is the number of ways. I don't have to sit here and write every single number out. So case 1, case 2. So without replacement, order matters. First thought, how many possible ways we have? Or second, third,
2,
fourth,
-3,
last one,
-k-1 with parentheses, r-1 parentheses. I guess it'd be r-k+1.
or minus k plus.
No. 4 plus 1. Oh, that's r-k-1.
Is that or minus k minus 1?
Yeah, because you'd have to take the plus 1 out of parentheses. It'd be r+1 minus k. Like 3 plus 1 is 4, r minus 4. That's the same, so.
So or minus k plus 1. Yeah.
That works.
That's what I wrote. Did I not?
No, they're in parentheses, they're on the k plus 1.
Let's see.
That's what I meant.
Okay. Now, I forgot your name.
What?
I knew it started with D. I was about to call you Dusty. Okay. So he said it was k r factorial divided by. Or is it k factorial divided by k minus? R factorial divided by r, is it going to be k minus r or is it r minus k? R minus k. Do we know what a factorial is?
Yes.
Okay.
I think,
Do we all know what a factorial is? Okay. So I can jump directly to what I have to say. Now, why is that true? So we are trying to make sure that order matters and it's done without replacement. So we want to know the number of ways it could happen. So we wrote this out, but this is equal to that. And that simply is what we call N to R. National Public Radio.
I was about to say that.
So what does a P stand for? P stands for permutation. So we are simply finding the number of possible orderings, just like the previous case, but only this time, what's the difference? It's without replacement.
Yeah.
Last time it was with, now without. How are those to equal? The numerator, R factorial simply means 1, 2, 3, all multiplied, right? I'm going to go all the way up to some number, R minus K. And R minus K is going to be less than R factorial, right? That's a requirement. So we'll have R minus K plus 1, R minus K plus 2, because this term plus 1, this term plus 2, you are moving forward you're going all the way up to what? Has to be R. We go all the way up to R. This is not NPR, it's RPK. I just got excited. So R factorial divided by R minus R. I just wanted to make the NPR joke. It was that, but still. The denominator is R minus K factorial. So we would have R minus K factorial. The numerator that part, what does that look like?
R minus K factorial.
R minus K factorial. What happens to that and that?
They cancel.
They go by R. Look at that, and look at this. Are they one and the same? Yes. So it's just a different order, but we all know 2 times 3 is the same as 3 times 2. Okay, just checking. So instead of writing it in an elaborate way, we simply call it as a permutation. If someone came up to you and said, okay, I have all different items, and you get to pick 3. I make sure that all of them are distinct, they're not similar, they're all unique, and you get to pick 3 and put it in 3 sequences of 3, and you order them out. You don't have to sit and write them out, you can just put it in here. Because if someone came up to you and said, I have, let's see, 26 balls with the letters, in the alphabet, A through Z. And you get to pick 5 of them up front. And you have to form sequences of 5. Order matters, right? Do you want to sit there and write all of those? No. But we'll know the number of ways, since it is without replacement. For instance, the moment A is taken out, how many letters will I have? 25, then 23, and so forth. So originally you had 26, then 25, 24, 23. Or you can simply put it in this formula, 26p prime. So your calculator does 26p prime. Right? Does that make sense? Yes. Okay. That's a good place to stop.